Hello friends, I am Dr. Sangeeta Patil, Assistant Professor in the Department of Electrical and Electronics Engineering, MIT School of Computing, MIT ADT University. Welcome you all for a course on Basics of Transformer. Let us start the lecture. So let us start with the polarity of the transformer. Students, we know that the transformer works on the principle of the mutual induction. The direction in which the windings are wound, that only decides the polarity of the mutually induced EMF. But practically it is not always possible to draw the coil as per their winding directions. Hence, to indicate the winding directions in the transformer, the dot conventions are used. If the two coils of are mutually coupled, then the terminals which are bearing the dots will be having the in-phase induced voltages. The dots are marked on both the windings of the transformer as shown in this figure. The dots are marked on both the windings, that is primary and secondary winding, which indicates the similar polarity ends of the two windings. Similar polarity ends of the two windings are those ends which becomes positive or negative simultaneously when the EMF induced in them is same. Or in this figure we can say that this A1 and small a1 are becoming positive or negative simultaneously. Okay. Then question must be in your mind that how to test the polarity of the transformer or how to test the polarity of both the coils, primary and secondary coil, in the actual practice. So let us start with the polarity test. So students, polarity test we have to perform on the transformer to determine the polarity of the windings. So this is the figure which is drawn for the polarity test. Polarity test is carried out in order to determine the relative polarity of the two windings of the transformer, that is primary winding P and the secondary winding S. The setup of the polarity test is shown in this figure. Okay, it shows that the two windings are connected in series and a voltmeter, it is connected across their series connection. So the equivalent circuit of this figure, A figure, is shown in figure B. These two windings are connected in series and voltmeter is connected across their series combination. If the polarity of the windings are as shown in figure B, then voltmeter reading I will write here. V equals to V1 minus V2. Why it is like this? Because here two windings are connected in series like this. So if we apply Kirchhoff's voltage law to this loop, this voltage, if I take it as negative minus V2, it will become plus V2, V1. Means this voltmeter, if we indicating the difference between the two voltages, V1 minus VT, means the polarity marking of the transformer is like this, means dot. Both the ends of the two windings are becoming positive or negative simultaneously. And if the voltmeter reads V is equal to V1 plus V2, means that we have to change the polarity of the one of the winding. So if the voltmeter reads V1 plus V2, then the polarity marking of one of the winding should be interchanged. In this way, the polarity of the two winding transformer can be identified. Okay. So now, what is the necessity of the parallel operation of the transformer? These are the three main reasons why the parallel operation of the transformer is needed. The first reason is the higher reliability. Student, if we are using the single transformer, then if its failure will be there, it will automatically shut down the total installation. If a parallel transformer is connected in parallel with the first transformer, then the parallel transformer will solve this problem and hence improve the system reliability. The second reason is better maintenance and the repair. It is possible to repair or maintain the transformers in parallel connection one by one without shutting off the whole plant. And third reason is it is very easy to make addition in the existing setup. With increase in the load current, we can supply or add a new transformer to the existing parallel unit of the transformer system. So now let us see the parallel operation of the transformer. So here I have taken the two transformer T1 and transformer T2. T1 and T2 both are connected in parallel. For supplying a load in excess of rating of an existing transformer, a second transformer T2 is connected in parallel with the first transformer, that is T1. It is seen that from the figure the primary windings are connected to the supply bus bar, which are written here as a primary bus bar, and the secondary windings are connected to the secondary bus bar, which are called as a load bus bar. I will write down here load bus bar and I will write down here supply bus bar. In connecting two or more than two transformers in parallel, it is essential that their terminal of similar polarities are joined to the same bus bar as shown in the figure. If this is not done, then what will happen? Then the two EMFs induced in the secondary coils, which are connected in parallel with incorrect polarities, what will happen? If this is not done, then the two EMF induced in the secondary, which are in parallel with incorrect polarity, will act together in the local secondary circuit, which is shown by the dotted red line in this figure. Even when this transformer is not supplying the load, this EMF which is induced in the secondary, that EMF will responsible for producing the dead short circuit as shown in the figure. Hence, the transformer should be connected taking their polarity into consideration such that the net voltage around the loop is 0. If the polarities goes wrong, then there will be a dead short circuit across the secondary bus bar or the load bus bar. Now let us see what are the different conditions those are to be satisfied for successful parallel operation of the two transformers. Following conditions are to be required to satisfied in order to ensure the successful parallel operation, or in order to avoid any local circulating currents in the secondary side, also to ensure that the transformers share the common load in proportion to their kVA ratings. So first condition is that the primary winding of the transformer should be suitable for the supply system voltage and the frequency. So the primary winding of the transformer, it should be suitable for the supply system voltage and the rated frequency. Second condition is that the transformer should be properly connected with regards to the polarity, and the polarity should be correct. If the polarities goes wrong, then just now I have told you that there will be a dead short circuit across the load bus bar. Third condition is that the voltage ratings of both primaries and secondaries should be identical, or in other words we can say that the transformer should have the same turns ratio or the transformation ratio. This will avoid no load circulating current across the load bus bar. Then fourth condition is that the percentage impedance should be equal in magnitude and they should have same X by R ratio in order to avoid the circulating currents and the operation at different power factors. With transformers having different kVA ratings, the equivalent impedances should be inversely proportional to their individual kVA rating. If the circulating currents that we have to avoid during the parallel operation. So these are the four conditions which are to be satisfied for successful parallel operations of the transformer. Now let us see, student, the parallel transformer on the no load. So this figure shows you the parallel connection of the two transformer T1 and transformer T2. The transformers are paralleled on both sides with the proper polarities. The primary voltage V1 and V2 both are equal. If the voltage ratios of the transformer are not equal, then the induced secondary voltage E1 and E2, those will not be equal, and the difference E1 minus E2 will appear across this switch S. When the switch I will close here, due to the difference of E1 and E2, the circulating current will start flowing due to the potential difference of E1 and E2. The circulating current of the transformer also depends upon the total leakage impedance of the two transformers. Dear friends, in order to control the leakage current, the voltage ratios of the transformer should be almost equal. We can tolerate only the small difference in voltage ratios for this reason, and that is the one of the most important condition that must be satisfied for the parallel operation of the transformer. Now let us see the division of the load current between the transformers in parallel. We have to consider three cases. First case is ideal case, then second case we will see that the equal voltage ratios case, and third case will be the unequal voltage ratios. So let us start with the first case, that is the ideal case. We will first consider the ideal case of the two transformer having same voltage ratios and having impedance voltage triangle which is identical in size and shape. Let E be the no load secondary voltage. E will be the no load secondary voltage of each transformer, and V2 is the terminal voltage, IA and IB be the current supplied by this transformer. IA is the current supplied by transformer A and IB is the current supplied by the transformer B, and hence I is the total current flowing through the load which is lagging behind this voltage V2 which is across the load by angle phi. Okay, so now let us draw the phasor diagram for this figure. So I will take V2 as a reference vector. Then my IA and IB both lags that voltage by same angle because they are connected in parallel. Okay, so this is your IA and this is your IB, and same is nothing but your I which is lagging behind my V2 by angle phi, power factor angle phi. In this figure, the single triangle, first of all I have to draw the triangle. So let us draw the IRA drop which is in parallel with IA. So this is your IRA drop, or IR drop, simply I will write down IR drop which is in parallel with the IA. And now let us draw the impedance drop. So IX drop which is perpendicular to I, this is your IX drop perpendicular to I, and vector sum of both drops and V2 will give me the EMF E of the transformer, and vector sum of IR and IX is nothing but IZ. So in this figure, I will mark this is A point, this is B point, and this is C point. So in this phasor diagram, the single triangle ABC represent the identical impedance voltage triangles of both the transformer. As impedance is same, current is same. So the IA and IB I have shown in the phase. The currents IA and IB of the individual transformer are in phase with the load because impedance triangle of both the transformer is same. and both are inversely proportional to their respective impedances. So student, I can write down here I will be equals to IA plus IB. IA plus IB. Simply I will apply the Kirchhoff's current law to the circuit shown here. Then what is my V2? My V2 will be equals to E, that is EMF of one of the transformer minus IA into ZA, which is equals to E minus IB into ZB, because impedances triangles are same. Or I can write down V2 is equal to E minus I into ZAB. What is ZAB? Parallel combination of ZA and ZB. Okay. Then also IAZA will be equals to IAZB. Yes, because both are connected in parallel. Or I can write down IA upon IB equals to ZB upon ZA. Therefore, we can say that the currents IA and IB of individual transformers are in phase with the load current I and inversely proportional to their respective impedances. So IA is inversely proportional to ZA and IB is also inversely proportional to ZB. Then if I apply current division rule to this loop, then I can write down the equation for IA and IB also. So what is my IA? My IA will be I into ZB upon ZA plus ZB. Current division rule. Okay. Similarly, I can write down IB. What will be IB? IB is nothing but total current through load into ZA upon ZA plus ZB, because my IB current is through ZB. So I will multiply it by with the opposite impedance on the numerator side. So these are the simple equations that we have. This is the ideal case we have assumed. What is the ideal case? Ideal case is that net voltage in this loop will be 0. So there will be no circulating current. Current flowing through the load will be the algebraic vector sum of my IA and IB. So we have to apply Kirchhoff's current law to this node. Okay. So now let us see the case 2. What is the case 2? Case 2 is the equal voltage ratio. Let us assume now that the no load voltages of both the secondaries is same. Means EA equals to EB equals to E. I will write down here EA equals to EB equals to E. This is the condition when we are talking about the equal voltage ratios. And the two voltages are coincident with each other. That is, there is no phase difference between EA and EB, which would be true if the magnetizing current of the two transformers are not much different from each other. If the magnetizing current are different, then obviously there is some difference between EA and EB. Under this condition, both the primaries and secondaries of the two transformers can be connected in parallel and there will be no circulating current between them on the load side or on the no load, we can say. However, if we neglect the magnetizing admittances, the two transformers can be connected as shown in this figure by their equivalent circuit, which is shown in the figure B. This is your figure A and equivalent circuit of your figure A is shown in figure B. From both figure A and B, it is seen that it represents the two impedances in parallel. ZA is connected in parallel with ZB. Considering all values consistently with respect to the secondary. So let ZA and ZB are the impedances of the transformer A and transformer B. And IA and IB are their respective current. V2 is the common terminal voltage and I is the total current or the combined current. So this will be your I in this figure. Current through the load. Current through the load. Okay, so now I can write down from this figure, I can write down IA ZA will be equals to IB ZB will be equals to I into ZAB. What is ZAB? ZAB is nothing but the parallel combination of ZA and ZB. So I will write down my ZAB equals to ZA into ZB divided by ZA plus ZB. Okay, this is your equation number 2. This will be your equation number 1. Okay, from equation what we will get? From equation I will get IA ZA equals to I into ZA B. Okay, therefore I can write down my IA will be equal to I into ZAB divided by ZA. Okay, or I can write down here I into ZB divided by ZA plus ZB. Why? Because just put up here the ZAB value. What is ZAB value? ZA into ZB from equation 2. Here put ZAB from equation 2 in above equation. Then we will get this. Okay. So similarly, this is your IA. This is your IA. Similarly, what I can write down? I can write down IB equals to I into ZA divided by ZA plus ZB. So simply we have seen these two formulas with the help of the current current division rules in the above figure also. Okay. So if I multiply both sides by the common terminal voltage of above two equation, then what I will get? I will get V2 into IA equals to V2 into I into ZB upon ZA plus ZB. I have multiplied both sides of this equation by V2. Similarly, I will multiply both sides of this equation by terminal voltage V2. So V2 IB equals to V2 into I divided by into ZA divided by ZA plus ZB. Now students, we know what is V. Just a minute. What is V2 into I into 10 raised to minus 3? That is nothing but the KVA rating or apparent power or the combined load KVA. That is the combined load KVA of the parallel combination of the two transformer. Then the KVA carried by each transformer. This is the KVA carried by A transformer. This is the KVA carried by B transformer. Therefore, I can write down. Hence, I can write down SA, that is KVA rating of first transformer, SA, from this equation. What is this? This is nothing but S. This is nothing but S into ZB upon ZA plus ZB, right? Or I can write down this as S into 1 upon 1 plus ZA by ZB. If I divide both this, means this by ZA. Okay, this by ZA. Similarly, I can write down SB is equal to S into ZA divided by ZA plus ZB, which is equals to S into 1 upon 1 plus ZB by ZE. So these are very important equation which will require to solve the problems. What is this? This is nothing but your SA. This is nothing but your SB. And what is V2 into IA is nothing but the combined load kVA of the parallel combination. So from the total combined load kVA, we can find out the individual kVA of each transformer. So this is the kVA of transformer A, this is the kVA of the transformer B. Hence students, SA and SB, that is the kVA rating of transformer A and kVA rating of transformer B, are obtained in magnitude as well as in phase from the above vectorial expressions which I have written with the help of equation number 3 and equation number 4. Now let us see the third case, that is the unequal voltage ratios. Unequal voltage ratio. In this case of unequal voltage ratios, the voltage ratios of the two transformers are different. It means that their no load secondary voltages are unequal. Such cases can be easily handled by drawing the phasor diagram, right? So let us draw the phasor diagram. Before drawing the phasor diagram, let EA and EB are the no load secondary EMFs of transformer A and transformer B respectively, and ZL will be the load impedance across the secondary. The equivalent circuit and the vector diagram we can draw. So let us draw the phasor diagram. For drawing the phasor diagram, I will take V as a reference vector. I will take V as a reference vector. Okay, then current IA and IB both are not equal. So let us, this is your current IA and IB is more inductive than IA. So this will be your IB. Then what is your total current? Total current is nothing but vector sum of both. Total current is nothing but vector sum of both. So I will take vector sum of IA and IB, so that I will get the load current, that is current flowing through the load, which is equals to I. Which is equals to I. And angle between V and I is nothing but always the power factor angle phi. Now, first of all, I will draw the impedance triangle for A transformer. So parallel to IA, I will draw the IARA drop. IARA drop. And perpendicular to this, I will draw the IAXA drop. And vector addition of both is nothing but IAZA. IAZA, IARA and IAXA. Now with the red color I will mark for IBZB. So parallel to IB, I will draw the, this is your IB RB. Then perpendicular to this, this will be your IBXB, and vector addition of both will be IBZB, right? But in actual, what is the EMF? EMF is nothing but vector sum of IAZA and V. So let us, for A transformer, I will mark this as your EA. What is EA? EA is nothing but V plus IA ZA, right? And EB is nothing but V plus IB ZB. So let us mark this with the red color line. So V plus IB ZB is nothing but your EB. It is nothing but your EB, EMF induced in the B transformer. So from this it is seen that even when secondaries are on no load, there will be some cross current in them because of inequality in their induced EMF. Okay, so the circulating current IC, the circulating current, let us see it as a IC, that will be equals to EA minus EB divided by ZA plus ZB. Because my voltages are not equal, so on the load side there will be the phase difference of EA and EB, and hence some circulating current will be flow through the secondary side. As the induced EMF of the two transformer are equal to the total drop in their respective circuit, I can write down EA is equals to IA into ZA plus V2, right? Similarly, what is my EB? EB is nothing but IB ZB plus V2. Now what is my V2? V2 will be equals to I into ZL, I into ZL. So what is I? I is nothing but IA plus IB, vector sum of both into ZL. What is ZL? ZL will be my load impedance. ZL will be the load impedance. Therefore, I can write down EA equals to IA ZA plus, what is EA? IA ZA plus V2. So what is V2? V2 is nothing but I into ZL. But what is I? I is IA plus IB. So I will put the value of V2 here in terms of IA and IB only into ZL. Then this is your equation number 5. Similarly, I can write down for EB. What is EB? IB ZB plus V2. What is V2? IA plus IB into ZL. Let us, this is your equation number 6. Just a minute, students. I will write down this properly. Okay. So now, if I subtract equation 6 from 5, then what I will get? EA minus EB on the left hand side, and on this side I will get IAZA minus IBZB. These two terms will get cancelled. Let it, this is your equation number 7. Okay, from this I can find out IA. Yes, what is IA then? IA will be EA minus EB plus IB ZB divided by ZE. Now, let us, this is your equation number 8. Let us, this is your equation number 8. Put value of IA from equation 8 equation 6. So what we will get? EB equals to IBZB as it is, plus in bracket I can write down EA minus EB plus IBZB upon ZA plus IB into ZL. So what is IB from this? IB from this we will get equals to EB into ZA plus minus EA minus EB divided by ZL upon ZAZB plus ZL into ZA plus ZB. And if we apply the symmetry of this equation for finding out IA, I will get the next equation, that is for IA. So what is IA? If we apply the symmetry, what we will get? Instead of EB, EA will become, instead of ZA, ZB will become, plus in bracket EA minus EB divided by ZL, this remains same, divided by denominator also remains same, that is ZAZB plus ZL into ZA plus ZB. That this is our equation number 10. Also we can find out I. What is I? IA plus IB. So if you put the value of IA and IB from equation 9 and 10 in this, you will get I equals to EAZB plus EBZA divided by ZAZB plus ZL into ZA plus ZB. So simply we have to add equation number 9 and 10 to get the current I, that is the total load current. So this is about the transformers in which we have considered the three cases for the division of the load current between the transformers which are connected in the parallel. So we have seen how the polarity and the voltage ratios of the two transformer matters the parallel operation of the single phase transformer. Students, in my next lecture we will start with the three phase transformers. So if you like this video, please don't forget to like, share and subscribe my YouTube channel. Thank you.